So in this lecture, I'm going to touch on some Lewis acid mediated transformations, as these are related to reactions under acidic conditions. So to start, let's talk about some good Lewis acids. And we'll start with POCl3. Whoop, goodness. POCl3. Okay, the structure of this is has a phosphorus-oxygen double bond and then 3 chlorine atoms around the phosphorus atom. It turns out that this structure is tetrahedral at phosphorus, and phosphorus is able to form this pi system to the oxygen atom because it is a row 3 element and can have an expanded octet. Turns out the phosphorus-oxygen pi bond is very strong. Sort of providing insight as to why this structure can actually be formed at all. We also have another phosphorus species to consider, and that's PCl5. So both of these reagents are really good at attracting oxygen atoms, along with other nucleophiles, because the chlorine atoms serve as leaving groups. They're also both what we call phosphorus 5 atoms. That is, phosphorus is in the 5th oxidation state. It has sort of at least 4 negative, well, I guess in the second case, 5 negative 1 charge things, and then 3 negative 1 charge things in the chlorine atoms, and then the oxygen atom is a negative 2 charge things. They're both in the 5th oxidation state. So these are, just in general, phosphorus 5 is a good Lewis acid, especially when bonded to chlorine or other halogens. Okay, now we'll get into some metals. Moving away from main group elements like phosphorus and the other things, let's get into the transition metals like iron. So in particular, iron 3, iron in the 3rd oxidation state, and we've used things like FeCl3 and FeBr4 in organic 2, FeBr3, excuse me, and FeCl3. But there's also FeAc3. It's a really interesting ligand attached to the iron atom, where you've got an acetyl acetone is what it's called. And the dicarbonyl nature creates an enolate in the at the central carbon, which is shown by this oxygen with a negative charge. And this is the binding site for the metal. But we get some additional bonding sites from the other lone pairs on the other oxygen atom, providing a stabilizing interaction. So this is a pretty interesting source of iron 3. It's a little bit more stable than FeCl3 and FeBr3, allowing us to get iron 3 into more versatile, allowing it to be more versatile in its ability to get into solution under some interesting conditions. There's also tin. Tin is a big version of carbon, I suppose. It's pretty big. So tin 4, and what we can do is we can take tin and surround it with chlorine atoms, and just like phosphorus atom, now we're highly reactive under these conditions. And chlorine seems to be sort of the name of the game in terms of making things really good Lewis acids, particularly with oxygen. We can have zinc chloride. I guess we don't need parentheses. I'll just cross those out. So it's just, sorry, that bothered me. Okay, zinc chloride. So this is a zinc 2 source. I suppose I'll write that up here. So zinc 2, tin 4, iron 3. These various types of metals, we're going to see a whole section of reactions on transition metals, but they're not going to focus on this Lewis acid nature. They're going to focus on some other things, some other interesting transformations that can occur with the transition metal being present. Again, these are Lewis acids. That is, they sort of serve like a big proton with different selectivities than hydrogen. So they are less reactive with some things, more reactive with other things when compared to a hydrogen cation. Okay, just some thoughts about tin-4 really quick. I'm just going to mention is it's highly toxic. It turns out this is a really great reagent for a number of applications. It has a super weird smell. The fact that it has a weird smell is not good. Why do I feel like I know that tin is a cumulative toxin? I think that's a thing. Gosh, that's kind of scary. So an acute toxin means if you consume it some amount, you could die, bad, right? But you could also survive. And if you survive an acute exposure to an acute toxin, your body will likely be, for the most part, no worse for wear once everything's kind of been metabolized and excreted. However, if you have a cumulative toxin and you're exposed to some, but not enough to kill you, that actually makes it so the next time you get exposed to the same amount or even a less amount, you could die because you will accumulate this toxin in your body, also causing some other nasty side effects. And tin is a cumulative toxin. In fact, tin, it's still versatile because it has many properties similar to carbon. So there's a big manufacturing industry surrounding it. Things are better now, but it used to not be the case. And workers would come home. Like I said, it has this weird smell. And I'm sad I know that smell because that means I've probably been exposed to some. But workers would go home and they'd smell tin everywhere, including a really strong odor from their urine, which is definitely not good because if it's in your urine, then your body's desperately trying to metabolize it, and it's not. Anyway, so tin-4, good, good Lewis acid. Let's move on. Getting back to the science at hand, there's also non-metal groups like acyl groups. So here we're going to have our Lewis acidic atom be a carbon atom. So we could have this molecule is a good Lewis acid. It will interact with the Lewis base, a lone pair of electrons on something. And then another great one, if we're looking at just, excuse me, Lewis acidic electrophiles, we have oxalochloride. This is named for the fact that it's an acid chloride derived from oxalic acid, the first dicarboxylic acid in that Oh My Such Good Apple Pie series or mnemonic that we had talked about, I think in organic too. Group 3 elements like aluminum make for great Lewis acids, so AlCl3. So this is aluminum 3. And then boron 3. Oops, I flipped the names. All right, parallelism, not on my side today. So you could use BCl3 or BH3. Both of these are strong Lewis acids. Titanium 4. So titanium 4, and then a common source for titanium 4 is titanium tetrachloride. Titanium bound to 4 separate chlorine atoms with a neutral charge means that titanium's in the 4th oxidation state. If you want to get really uncomfortable, you could work in an industry, work at a company that uses this all the time because people will say things like, hand me the tickle 4. And you're like, what? What on earth is tickle 4? And that's titanium tetrachloride. But anyway, kind of a funny way to describe a chemical reagent, but that's what they do. Okay, so, oops, I need a new page. And so lastly, we could have dihalides like X2, and that would be Cl2, Br2, and I2. So here are examples of a bunch of Lewis acids. And what I'll just say is that what you'll notice about all of these is that they're good electrophiles. And as good electrophiles, they're just going to engage nucleophiles, which have lone pairs. Well, in terms of Lewis acid context, those lone pairs are our bases, and these electrophiles that accept the lone pairs are our Lewis acids. Okay, so let's look at some examples of how we actually use these things. So we have PCl5 or POCl3, as we had talked about. These are really good dehydrating agents. That is to say, they remove H2O very efficiently. Okay. So if we look at some examples, what we could do is we could take something like an oxime. Here's an oxime and treat this with POCl3. And we get to something a little less unusual, much less unusual, and that's an amide. Now, how did we get there? Well, let's first recall that if we want to think about making an oxime, this is actually an organic 2 functional group, but it's towards the end. I don't blame anybody that maybe has let this slip their mind. But what you do here is you take a ketone and you react it with hydroxylamine. And this is in the class of transformations that can occur when a nitrogen atom with single bonds and typically 2 hydrogens engages a carbonyl. We lose water and the nitrogen swaps place with the oxygen, carrying only its non-hydrogen substituents along for the ride. In this case, it's the OH. So this is hydroxylamine, and that's readily available. But let's look at the mechanism for the amide formation. So we form an amide here. And so it turns out that just very generally, the Lewis acids that I had described have a very high affinity for oxygen, also fluorine, but it's typically not the case that you need to take advantage of that aspect. So the mechanism starts with the Lewis acid finds oxygen, or I guess fluoride, not usually fluorine bound to carbon, but fluoride floating around as an ion. Again, very uncommon. Okay, so let's consider the mechanism for this conversion of an oxime to an amide. The first thing we want to do is not draw POCl3 as POCl3. We want to draw it as the actual structure so we can picture what's going on here. So it turns out that in a structure like this, we're going to see similar behavior to a carbonyl, but not for the same reasons. We can go ahead and draw the curly arrows, though. I'm just going to add to the phosphorus underneath and push the electrons up and onto the oxygen atom. That intermediate is fairly short-lived as a trigonal bipyramidal structure. For the lone pair comes down, lone pair comes down and kicks out chlorine. Simultaneously, the hydrogen on the oxygen with the lone pair is lost. Okay, let's immediately push onward to the resulting structure. Okay, so the oxygen's lost its hydrogen atom, and the phosphorus has lost one of its chlorine atoms. And so what happens here, and I don't really know the protonation state of the oxygen, but what's proposed to happen next is that the phenyl group actually migrates up and onto the oxygen atom to give rise to a new carbon-nitrogen bond, and then it simultaneously kicks off the oxygen that is part of the phosphorus atom. Now, when we do that, we're left with something that looks like this. It's weird because I have to draw some linearity. I guess I don't have to draw linearity on the nitrogen, do I? So let's not draw linearity. Let's draw it as bent. But the carbon atom has a positive charge. And we could kind of show some stability there. Ooh, I guess I do have to consider a resonance structure. And if I consider a resonance structure, I see why the geometry has to be linear at nitrogen. So here's a more stable resonance structure where everything is neutral, and that implies then that this nitrogen must be linear along with the carbon. Both are sp hybridized. So if one resonance structure requires linearity, they all do. And that's just because nuclei aren't supposed to move when you consider resonance structures. Well, this is a really cool intermediate positive charge on nitrogen now because it can readily engage with water, either at the carbon in this resonance depiction or the carbon here pushing the electrons onto the nitrogen. You can get to any product from any resonance structure of the immediate precursor intermediate. Okay, that's going to give us an oxygen with 2 hydrogens and a positive charge. The nitrogen now has a phenyl group, or still has a phenyl group on it, excuse me. We can lose a hydrogen atom and then tautomerize to, I'll draw the enol out. I think that's healthy. So N-phenyl OH. This is the enol form of an amide, which undergoes spontaneous tautomerization with favorable equilibrium towards the amide. Okay. We did it. And we did it by letting the POCl3 basically remove oxygen from our molecule, which we could follow up with some addition of water. And this water probably comes in during the workup, implying that we're sitting here as a resting state during the course of the reaction. Okay, let's keep moving on to more and more transformations. I guess let's see a great stopping point. So I think I'm just going to kind of continue onward through and just look at numerous types of reactions that all involve Lewis acids. So let's look at an iron mediated example. Sorry, just crossed through the notes there. So, and let's analyze this to see if this is going to be an iron catalyzed reaction as opposed to an iron mediated reaction. But the overall reaction, and I usually just pull these from the book because the ones that look interesting at least. Okay, this is a tough thing to draw when I'm scrunched. So I'm just gonna, if you started drawing, I'm just doing the exact same thing. Just giving myself some room at the bottom of the page to show CO2 Me, then dash to an Me as part of a 5-membered ring with a cis epoxide. That we then treat with Fe, and we're going to go with AC here. AC. Should be all lowercase. I don't know if I did that earlier in the notes. Sorry about that. And then we get a 6,5 system. Ooh, with a methyl group now up top. And an OH up here. And then CO2 and Me hasn't moved, so we have that as sort of a placeholder to tell us what's going on. Well, interesting mechanism to say the least. Now, I said this was a Lewis acid mediated transformation. I know we've talked about Fe AC before, and it's subscript 3 because it's iron 3 plus 3 times. And then we're looking at this dicarbonyl species where one of the oxygens is negatively charged because we form a very stabilized intermediate enolate stabilized by the 2 carbonyls. So we have 3 of these, and these are -1 overall. We have 3 of them to counter each of the positive, 3 positive charges on the iron. Now what this looks like is an octahedral arrangement, which means we have 2 up, or excuse me, 1 up, 1 down, and then 2 wedges. Oops, there we go. And 2 dashes. Now, every atom that connects to the iron is an oxygen. It just so happens that sometimes they're double bonds and sometimes they're single bonds. So there's an iron that sort of twists and orients itself over the iron atom. So we could have double bond here if we wanted. And then we could have there. So one of the oxygens that's coordinated to the iron is a carbonyl. The other one is an alkoxide from the enolate. And we form an octahedral complex. Octahedral complex with 3 times the AC ligand, and that's again acetyl acetone. And why would you want to use this? It's a soluble and stable version of Fe3+. It's hard to get metals into organic solvents. You need the right ligand to get them there, but then you also need the ligands to not interfere or to help with the reaction that you're trying to actually study. All right, so let's now do the transformation. Turns out that just like other epoxides, we're going to see this iron atom be highly, what I should have used earlier, oxophilic. That is, it's oxygen loving, as most Lewis acids are. It's going to let a lone pair of electrons engage just the Fe3+. That's all I'm going to write. And we'll see this actually will be a catalyzed reaction. So it's not just mediated, it's a catalyzed event. But this is basically like a big proton that's specialized for certain nuclei. So when the epoxide gets to interact with the iron atom, we're going to get to a species like this. And I guess we could write 2+, but I don't really worry about it. Okay. Then what we're going to do is, using the stereochemistry, we're going to do a 1,2 methyl shift to pop open the epoxide. With good stereo control, to give rise to OFE. That's going to put a positive charge in a tertiary position, which is no big deal. And then the hydrogen is just going to eliminate to give rise to, I mean, if we look at that positive charge just a second, it's at a tertiary position and it's also in conjugation with an alkene, an electron deficient alkene, which isn't great, but an alkene nonetheless. So we could lose that, we could have that carbocation readily form if that methyl group looks to be like an awkward shift, but it's just sort of walking underneath the ring. It's probably not a big deal. So we can lose the hydrogen, form another double bond. And that gives rise to this structure, which just accepts a proton. So I'm just going to draw like an arrow going to that hydrogen. Now the iron's out of the way, it can go mediate or catalyze another transformation, CO2Me. Shoot, I've got the double bond in the wrong place. Okay. And now we've got our species plus Fe3+, which is regenerated, able to catalyze the next transformation. Okay, I think we've got a few more reactions, but I feel like I'm just going to, we'll just take a break and then we'll look at other sort of reactions with strong Yeah, we'll look at some other reactions here in just a second. And we'll continue the trend of looking at metal-mediated transformations.